There we go. Testing, testing. Okay, there we go. There we go. I think it actually works now. Okay. All right. Plugging it in and taking it out apparently seemed to work. Okay. So let me just go ahead and start. I'll just start answering questions, and let's see. So Guntner says, "Hi Brian, having a regression model with a factor variable that has two levels, let's say A and B. A is the reference level, and B is a different one. Anyway, B has p-value 0.05. How can I justify p-value greater than 0.05? How can I justify including the variable?" Okay, so that's a great question, and let me get my file. Okay, so I think I might be able to just talk my way through this one. So whether or not to include a regression variable in a model is kind of a complicated topic. So just because your p-value is larger than 0.5, it doesn't necessarily mean that you want to omit that variable from your regression model. Let me give you an example. Imagine that your factor A is a control condition and B is a treatment. And the whole point of what you're looking at is to test whether or not the treatment is effective. Now what that p-value is telling you is it's giving you some evidence about whether or not the treatment is effective. But you always would want, regardless of the regression model, you would always want to include that in because that's what you're studying, right? Because that's exactly what you're studying. So there's no point there's no point in doing model selection at that point. You're not doing model selection. You're trying to do a scientific investigation of this treatment, and there's no reason to ever fit a model under that context without the treatment included in the regression model. So there's one example where the p can be larger than 0.05, but you would of course want to include that component in the regression model. A second instance is where, let's assume that you have another variable, let's call it t, that's a treatment effect, and your A versus B is a confounding variable, okay? So now you want to investigate a treatment, let's say it's a treatment for lowering blood pressure. Okay, so you have a blood pressure treatment, T versus not T. Okay, and then you have another variable, which is maybe whether or not this person, what's related? Let's say race. Race is often considered to be associated with blood pressure. Okay. Now, even if your race variable, A versus B, even if it's not significant, you might want to include it in that model because the estimate from including it changes the coefficient for your treatment variable. So even though that treatment effect or that race effect is not significant, you might want to include it in because as you're doing this scientific investigation, you want to look at the impact of treatment conditioned on race. Okay? So there's another instance where even though the p-value is larger than 0.05, you don't necessarily want to remove that variable from the regression model. What you're talking about, I think, when you start talking about putting things in and out of a regression model is an instance where you're not exactly sure about what to include or what not to include, and you want to come at a final model for some prediction setting or something like that. And if that's the case, then I would, start working. Even then, I wouldn't use p-values to decide what to include in the model or not. I would use, some machine learning thing or some model selection procedure. Or even if you did p-values, you're kind of doing it in an ad hoc sense where you're sort of playing around with the models, but really how you're adjudicating the model fit is by cross-validation or something like that. So at any rate, I can say there's numerous instances where you could have a large p-value and still want to include a variable in a regression model. And most of those concern instances where you're doing some sort of scientific investigation or some sort of investigation where you really care about the coefficients that you're getting out. the times where I think you don't want it is all these kind of machine learning instances, or prediction type instances where you're trying to automate the model fitting and you really don't care about what variables are in the model or not. Then I think, you know, then it's not clear that just looking at p-values is the right thing to do either. Then, okay. So anyway, nice question. Very interesting. I think it's a very interesting topic. And I just want to reiterate, and I hope what you're getting the sense when I'm talking about this is that regression is a tool, and just like a screwdriver, it has many uses. Yes, you can use it to screw in screws, but if you have a flathead screwdriver, you're always using it to pry open things and do all these other uses for it. And regression is just like that. So whenever you talk about what you're doing in regression, you have to talk about what your goals are. Okay. Oh, good. And someone said they can hear me now. Okay. Okay. I think everyone can hear me now because I actually see the the little bar saying that the audio is coming on. Okay. So how do we interpret p-values from ANOVA? I get low values for a comparison of two models regardless of the order inside the ANOVA function call. Order inside the ANOVA function call. I'm not clear what that means. I would have thought one order would be high and the other one. Let me just see if I can figure out what the question. So first of all, okay. Someone's saying the echo is driving them crazy. Let me trying to think of. I'm wondering if this is a connection problem or if this is. Let's see. Can other people tell me if they're hearing the same echo? By the way. I'm wondering if anyone's hearing the same echo. If lots of people are hearing it, I think maybe the solution is to stop and restart the broadcast. Let's see. Let's see down at the bottom here. Let's see. So at any rate, the echo. There's no. Okay. So I think maybe. Not sure what's going on. Okay. Darn it. So I selected away that other question. But let me answer that. The question was, what is the impact? Or the question was really about audio, about ANOVA and different strategies for fitting ANOVA. And I see that there's another question down here, and it says, can you talk more about ANOVA? But I'm having difficulty finding it, so I won't pull it up. But so ANOVA is so if you have a single factor ANOVA, that is the comparison of the name ANOVA stands for analysis of variance. And if you have a single factor ANOVA, like in the lectures, we had these insect spray example. You have a variable that takes on a couple of levels, and you have the mean, the number of insects, say, that died for each insect spray. And ANOVA looks at the variation in the means, the variation in the number dead by each level relative to the variation within the means. And let me draw a picture. Let me draw a picture that will hopefully elucidate this. Okay, so here's our box plots, and this is historically why ANOVA gets the name analysis of variance. So here's some outcome measure, and here you have a factor now with 3 levels. Okay, so let's consider two circumstances. Okay. Here's another set of box plots. Okay, in this case, there's a lot of variation. If you were to compare the means, there's a lot of variation between the means. And then if you were to look within the group, there's relatively little variation within the group. So what ANOVA is testing is it's testing the variation between the means, the between mean variation, relative to the within mean variation. And that's why in this case you would get a significant effect. In this case, right, you have a lot of within group variation and you have very little between group variation. And so in this case, you would not get a significant effect. Okay, and so I think in the question, the person was trying ANOVA, and it gets more complicated as you add more factors, and there's a collection of rules for when you include two factors, but there's no interaction, and then you include an interaction, and so on. So that's ANOVA for analysis of variance. Then there's this function in R called ANOVA, and the reason is it because it gives you analysis of variance tables. However, it does more than that. In general regression problems, it gives you the likelihood ratio test when you compare between two models. Okay, and so what I would suggest if you're going to use ANOVA in R, I don't find thinking about things in terms of ANOVA very helpful because I always have more complicated regression model settings than simple ANOVA settings. So, but I still use the ANOVA function in R, and the reason is I might have LM1 is a linear model that fits a y as a function of outcomes, a function of predictors, and I might have LM2 is a function of y and in the same set of predictors plus more predictors. Whether these predictors are factors or not, you can do in R ANOVA of LM1 and LM2. Okay, and it'll give you the f-test comparing the first model relative to the second model, and that is most useful when you have a model and then another model with more predictors added to it, and then there'll be a direct comparison as you move from the first model to the second model, and that's the p-value, for example, that you would want to look at when comparing the first model to the second model. At any rate, this function is called ANOVA, but it doesn't necessarily have to be exactly factor variables that you use to do it. So I think I wasn't 100% clear on the question, but my answer is there's two ways in which you can look at ANOVA. One is the definition of ANOVA, which is so-called analysis of variance, and it's looking at factor variables and comparing variation, and you can get at those tests exactly with linear models in the way we described in the class. And then there's this ANOVA function in R where you can put the output of a bunch of linear model or generalized linear model fits, and it tries to organize them in increasing parameter model spaces, and tries to give you f-test or p-values, or if you fit a GLM, it'll try and give you chi-squared values comparing the models. And this function, regular ANOVA, I kind of don't use that much because I just like to use linear models or regression. This ANOVA function I use all the time, and it's for things like model comparison. Though I would say if ANOVA, I think, if I'm correct, will spit out results if this model and this model have nothing to do with one another. I think it'll still spit out results. So you want to be careful. So in this class, at least what I'm willing to teach you is instances where you have a model with a bunch of predictors and then a model with the same bunch of predictors and more predictors, and then you compare those two. And the ANOVA for this will be exactly right. I would condition that if this has like 1,000,000 predictors and this has 1,000,000 predictors, you don't want to do this. But in ordinary settings where you have a couple of predictors here and then you're adding just a couple of more predictors, this all works out exactly right. Okay. Okay, sorry for all the questions. No need to apologize for the questions. It seems that regardless of the method of regression model selection, the initial term, intercept, as I assume what you mean, are more important than the end results. But initial choices seem most subjective. I'm not sure, again, I'm not 100% sure about this comment, but I'm assuming that you mean intercept, not interaction, okay? Um, and so in a GLM, and that makes a lot of sense that the interaction would always be super significant, right? Um, all the interaction is saying in a regression, right? Let's say you have data that you collected on incomes, right? And you have your starting income, I don't know, let's say is 10K per year or something like that, and your end income is like 200K per year for the data that you collected, and you want income, and you want something like health insurance expenditures. Okay, there's a reasonable question to look at. Do people with more money spend more money on healthcare, or do they spend less money on healthcare because they have better out-of-pocket, because they have better insurance or whatnot? So you got whatever relationship that would occur between those two things. All the intercept is telling you is that whatever model that you fit, if you extrapolate it down to zero, right? If you extrapolate it down to zero, that there's significant evidence that it's not exactly zero. That's all it's saying. So that's not a very interesting question, right? Because you didn't even collect data near zero, right? So it's not even an interesting question. If you want the intercept to be not significant, mean center your x's, and then your intercept will be non-significant. Mean center your x's and mean center your outcome, and then the intercept will be non-significant. So all the intercept is doing, and if you have a factor variable, right? You have, here's an instance where you have a three-level factor variable, right? Here's your factor variable, and here's your outcome, right? And here's zero down here. All this is saying, right, is that across all these guys, the average really doesn't look like, the average really doesn't look like zero. Or depending on how you've assumed your factors, if you give, say this is the reference factor, it's just saying the reference factor doesn't look like zero. But if you're measuring something that isn't near zero, let's say your outcome is height, right, and you're studying adults. No adult is zero height. So all it's saying is that no one's zero height, or the reference group isn't zero height, right? That's all that it's saying. So of course the intercept is always going to be super duper significant. And anyway, that's why it always comes up, and that's why it's not interesting. So anyway, when you see that 10 to the minus 100th on the intercept p-value, you can just kind of disregard that. It's irrelevant. Okay. What happens if the residuals are not normally distributed? That should affect the confidence interval and the coefficients. That's right. Okay, this is actually this is kind of a hard question. So the question basically boils down to, when is normality required to do regression? And your regression estimate is perfectly valid if your residuals are non-normal, if the mean regression relationship holds. So your coefficient should be fine. It's just that your coefficients are no longer maximum likely, are possibly no longer maximum likelihood estimates. But it doesn't mean that your coefficients are off, right? The least squares equation still kind of makes sense, right? So here's an instance. I can draw a picture. So here we have this, this relationship here, right? And what normality says is that at any given income level, right, that the data should fall in a normal distribution around it, okay? But you can imagine if the data fall in a gamma distribution around the line at every point, right, that this line that fit through regression would still be pretty reasonable, right? It would still tell you about the right. It would still tell you about the right distribution, or about the right coefficients. Now the inference changes depending on normality. Okay, the inference so the inference changes depending on the Gaussianity of the errors. If you have a small sample size, then you're kind of then unless you're willing to try some new things that are not ordinary regression like, then you're kind of stuck assuming normality or saying, oh, and then trying to get normality by virtue of transformations or deciding what variables to include or what variables to not include. However, if you have large sample sizes, there's actually generalized versions of the central limit theorem that say that your Gaussian confidence intervals and things like that for your coefficients are still valid even if your residuals are non-normal. Okay, so it's actually kind of a hard question what you're asking. What I would say is you don't need to stress about it that much if you have large sample sizes. Number one, what you want to be concerned with in your residuals is if there's patterns in your residuals. So patterns in your residuals are very, kind of systematic-looking patterns in your residuals are kind of problematic. But if there was a case like this, I would, and you had small sample sizes, then you might consider doing something like taking a log of your response, and that would maybe make your residuals look a little bit more Gaussian. But at any rate, for large sample sizes, you're protected against the non-Gaussianity by virtue of the central limit theorem type results. So anyway, but for small sample sizes, if you're actually doing inferences that depend on the Gaussianity, then you want to try some transformations. As an example, this would be a common setting. Actually, probably more than likely, right? It's usually that there's most people spending a little bit less, and then a couple people with super high expenditures. So usually these distributions are kind of heavy-tailed, skewed towards high values. And so, at any rate, this way, a log might help take care of it. And log, by the way, has many highly useful interpretation properties when you look at regression. So, at any rate, that's kind of a long-winded answer to that question, but it's more, my short answer is it's more complicated than just saying I need Gaussian errors, right? Okay. Okay, so back to Ron's question. So if we do ANOVA LM1 and ANOVA LM2, and ANOVA LM2, LM1 both have p-values less than 0.05. So to answer that, Ron, what I'm teaching in this class is the instance where you really where the models are nested. I don't. If the models are nested, I think my intuition is that reversing the arguments should give you the same answer because it orders them in terms of the number of parameters. So what I would say is if you're going to do ANOVA like the Anova function like that, then do it when LM1 is contained as a special case of LM2 where some of the coefficients are 0. And then the testing is very direct, and I'm confident it's right then. In instances where LM1 and LM2 are totally different models with totally different predictors, then I think kind of all bets are off, and probably you don't want to be using the Anova function anyway. So the question is, what if LM2 has interactions and LM1 does not? But so if LM2, the only difference is that LM2 has the interactions and LM1 does not have the interactions, then that's fine. That should work with the Anova function. Is it a must that you have to do correlations of your variables before fitting the models? I don't know. I would hate to just give a generic rule like that. But nonetheless, you should always do exploratory data analysis, which includes ordinary sample statistics. So yeah, I mean, so the short answer is, kind of always avoid canned rule-based statistics. You don't want to do statistics by flowchart. But on the other hand, always doing some exploratory data analysis it's very important. Yeah. So so yeah, I think you always do want to do some sort of, plots, correlations, means, variances. You always want to do that stuff before you start fitting models. Models are complicated, right? And that stuff is much simpler. And so it's basically, it's almost like doing warm-ups, right? Before you go do something complicated, you want to do some warm-ups and get it. But in this case, it's more than just warm-ups, because it often gives you a really good sense of what's going on before you start doing much more complicated model fitting. Okay, and then thanks for everyone for mentioning the echo. All right, let's see. Please explain the interpretation of summary fit for an LM with 2 categorical variables and 1 continuous variable. Okay, so let me. Yeah, I agree. It gets kind of hard as you add more stuff into these models. So let's say, let me think. So I'm going to do fit is a linear model, and my outcome is y, and I'm going to manually put in the intercept, okay? And then I have my a variable of interest. I have a variable of interest x, and I have f1, which is a 2-level. Let's just keep it as 2-level factors, and f2 is a second factor, okay? And everything's in the namespace, so I'm not going to put a data frame in there. And then I do summary fit. Okay, what you're going to get is you're going to get an output that says something on the order of, it's going to have your intercept, which we don't necessarily care too much about in most cases unless we've centered our x's. And then it's going to have x, it's going to have an estimate, it's going to have the coefficient, it's going to have the standard error of the estimate, it's going to have the t-statistic and the p-value in this, and then it's going to have probably, since our f1 I said was 2 levels, let's say the levels are 0 and 1, it's going to say f1 1, let's say, and then f2 1, which means, okay, so this corresponds to the linear model yi equals beta naught plus beta 1 xi plus let's say gamma I'll do beta 2. Beta 2 times the indicator that f1 is equal to is at the level 1 plus beta 3 times the indicator that f2 is at the level 1 plus an error term. Okay, so let's look at, so you get these coefficients, right? And let's look at what these coefficients mean. So this fit is giving you the estimate beta naught, beta 1, beta 2, beta 3 from this model. Okay, so what is beta naught? So beta naught is, and then I can get rid of my error term if I write this as the expected value of y, not the observed value of y, but the expected value of y, the average value of y. Okay. Okay, so what's beta naught? Beta naught is the expected value, expected response when x equals 0 and f1 equals 0 is at the reference level, and f2 is at its reference level. And we can see that because what would we have to do to get beta 1 out of this equation? We would have to plug in 0 for x. This term here that's only 1 when f1 is 1 would have to be 0, so that would mean f1 would have to be 0. And this one, when f2 is 1, would have to be 0. Would have to be 0. So that's only true when f2 is 0. Okay, and so if all those are true, then it doesn't matter what beta 1, beta 2, and beta 3 are. That's 0, that's 0, and that's 0. And so then you get beta naught. So the intercept in this case is the expected response when x equals 0, f1 equals 0, and f2 equals 0. So the intercept may not be very meaningful especially in the case where x equals 0 doesn't mean anything. If it's like weight, right? No one's 0 weight, or height, no one's 0 height, or something like that. Okay. Now beta 1, right? How do we get beta 1? So imagine the instance where let me just say expected value of y. This, I'm going to write out some notation. This is the expected value of y given x equals little x. Okay? Let me take this. Where x equals little x plus 1 minus the expected value of y, where x equals little x. Okay? So what I mean by that is, given the model, what's the expected average value of y given x takes the value little x plus 1 versus the hypothesis that x takes the value little x. Well, let's plug in. Okay, so that's going to be beta naught plus beta 1, and then now x is going to take the value x plus 1 plus beta 2, and I didn't tell you what f1 and f2 are, so I'm just going to leave that as indicator f1 equal to 1 plus beta 3 indicator f2 equal to 1, because I didn't tell you what f2 was. Okay, so that's this part. Now let's talk about that part. So minus, then beta naught, and then now in this case x is equal to x instead of x plus 1, and then again this stuff again, beta 2 indicator f1 equal to 1 plus beta 3 indicator f2 equal to 1. Okay, now if you look, and when we subtract these two, that cancels out, right? That cancels out. That cancels out. Those are the same. Okay, and notice this works out to be beta 1 x plus 1 minus beta 1 x, which is just beta 1. So what is beta 1? So beta 1 is then the expected value of the response given a 1-unit change in x, expected of the change in the response given a 1-unit change in x holding my first factor variable and my second factor variable constant. But it doesn't matter whether they're 0 or 1, it just matters that they're constant. Okay? And so that's what beta 1 is. Okay. Now let's interpret factor 1, factor level 1. Okay. Let's see. So factor level 1, right? That's this guy. So let's look at, I'm going to write this out again. Expected value of y given x is little x and factor value 1 is the value 1, factor value 2 is whatever it is, minus the expected value of y given x takes the value little x, factor value 1 is 0, and factor value 2 is whatever it is. Okay? I'm going to plug in for this guy right here, and I get beta naught plus beta 1x plus, in this case, factor level 1 is 1. So this indicator, what I just wrote out as an indicator function there, that's 1. Okay? So that's beta 2 plus beta 3, and I didn't tell you what factor value 2 is, so I'm just going to write it in as indicator whether or not a factor value 1 is 1. And so this function takes 1 if factor value 2 is 1 and 0 otherwise, minus beta naught plus beta 1x plus, now in this case, if this factor value is 0, factor value 1 is 0, then that term goes to 0 and the beta 2 doesn't show up. Okay, so 0 plus beta 3 times indicator factor value 2 is 1. Okay, so when we subtract these two, and it's subtraction of this, so when we subtract these two, that's the same, okay, that gives me a beta 2, right? That guy minus that guy gives me a beta 2, and then that and that are the same. Okay? So what is beta 2? Beta 2 is the expected change in the response holding f, the second factor, and x constant, comparing factor 1 equals 1 to factor 1 equals 0, where this is the reference level. Okay? So what I would say is, for your given problem, write out this guy and go through the exercise that I was just going through. And as you do, so if you do this enough, then you get to the point where you just kind of remember the little rules and tricks. But until you do it enough, you just kind of have to keep writing it out and coming up with these little things. So the point being is that every coefficient in a regression model is interpreted as the expected change in y as that variable changes, holding all the other variables constant. Okay, whether they're factor levels or not. Okay, now things get a little bit harder. Things get a little bit harder when you have interactions, which goes to Dorcas Nudati's question here. Sometimes interactions confuse me, and I would say interactions confuse everyone. So what you want to do when you have interactions is being very careful about interpreting them. Okay, so let's just go through one interpretation of an interaction. So let's go, if you have an interaction in a regression model, let's say if you have an interaction between a regression variable, so we have expect a value of y is equal to beta naught plus beta 1x plus beta 2 times a factor variable, factor 1. And now I'm just going to quit writing that indicator variable. Factor 1 is going to be 1 or 0. And so plus beta 3x times factor 1. Okay. What happens if factor 1 is 0? That term goes away, and that term goes away, and you get a line. This line is beta naught plus beta 1x. Okay, and here's the x equals 0 line. Okay, and then what happens if f1 is 1 rather than 0? Well, if this term wasn't there, then we would get beta naught plus beta 2 plus beta 1x, right? And you would get that the intercept changes, but the estimated slope, the estimated slope would be different. But all that it's allowing to do is move the line for when factor 1 equals 1. All it's allowing is for these two to be different in that regard. When we have an interaction, right, it's not only when this term is right here, when that term is not necessarily, when the beta 3 is not necessarily 0, then we get beta 1 plus beta 3x, and then we get this line, right? We can get this line. So this is the line beta naught plus beta 2, and then plus beta 1 plus beta 3x. Okay? So what is beta naught plus beta 2? Well, that's the intercept, right? So beta 2 is the change in the intercept between the two fitted lines. Okay? And then what's beta 1 plus beta 3? Well, that's the slope of the new line. So beta 3 is interpreted as the change in the slope comparing the instance where factor 1 is 1 versus factor 1 is 0. Okay? So that's one example of interpreting an interaction. This interaction right here, it would be interpreted as the change in the slope. Now, if you had other variables, it would be the same interpretation, but holding the other variables constant. So that's one example of interpreting an interaction when you have two lines. So I think if you want a context around this example, so I think in our thing we looked at miles per gallon as it relates to, I don't know, weight of the car, right? And you might have a 4-cylinder car versus a 6-cylinder car or something like that. Now it wouldn't have a relationship like this for that setting, but basically what the interaction is saying is it's saying how much does the linear relationship between miles per gallon and weight change? How much does the slope of that relationship change when comparing 4-cylinder to 6-cylinder cars? That's what the interaction would be telling me in that case. Okay, so let's see. I read that omitting a main effect while having interaction terms in a regression model is bad. Should I keep? The conventional wisdom is to keep the main effects in if you have the interactions, unless you really know what you're doing. I would say, this, first of all, what this boils down to is another model search question, right? So if you're doing model selection and the main effect is not significant but the interaction is, then it depends again on your goal. If you're doing prediction and you simply don't care about your end model, you only care about prediction, then it doesn't matter whether you follow these sorts of rules or not. What matters is what produces the best validated in terms of avoiding overfitting cross-validation type rules. But then again, I would say you would want to then have a you would want to approach the problem differently than testing p-values in a regression model or something like that. If you're doing some sort of scientific process, then in general you do want to include the main effect when you include an interaction for the purposes of interpretation. So I think, again, it's one of these questions that depends on context tremendously. But in general, if you're fitting a regression model where you want to interpret the interaction, so I mean, just as an example, take this one that we just worked on. What would it mean to exclude the main effect? That would mean that you were forcing the first line to be horizontal, right? And you want to test whether the second line is not horizontal, which is fine. That's a reasonable question to ask, but you need to be kind of in a specific setting to want to do that, and you would have to kind of know that's exactly what you'd want to do. Whereas if it wasn't, if you weren't quite sure that the first line was exactly horizontal, you wouldn't necessarily want to do that. So at any rate, the long and short of that question is, I think if you're doing regression modeling in the way that we like to do it in the class, which is to try and develop parsimonious interpretable models, I think in general probably you do want to include a main effect when you do include an interaction. But anyway, excluding the main effects, it does that, right? It forces certain, in this case, for example, it forces certain lines to be horizontal, or it forces, if it's kind of an Anova type setting, it forces certain means to be 0, right? Certain population means to be 0, right? And so unless you're quite certain that those means really are 0, you shouldn't be doing that. And that changes, right? So just think of here again. Imagine you fit two versions of this model. One where you used f1 equals 0 as the reference level, and one where you used f1 equals 1 as the reference level. Omitting the main effect assumes that a different level of x has a horizontal line as its response predictor relationship. So you need to be very careful in omitting main effects, because it may be the case that, you know, the idea that for level f1 equals 0 or for level f1 equals 1, a horizontal line just doesn't make any sense. And so anyway, so you want to be careful with doing that. You know, but if you really know what you're doing, right, if you understand all these principles, then there are times where you might want to do that. Okay, can you explain how to interpret a binomial GLM with a binary outcome and a single factor predictor variable? Okay. So what is it? So your outcome. So let's see. I was just before I started office hours talking with someone who has this so-called stop trials, and what they were doing is they were waiting until someone pushed a button, right? So, and sometimes, but they were trying to trick them, right? They were flashing go and stop signs. It's like that. They were kind of doing this version of like the little kids game of red light, green light. So they were doing like that, and sometimes you stop and sometimes you don't, right? And so they had their y was whether or not the person stopped, y equals 1 or 0. And then they have an x, which is sort of like how tricky they were being, right? In that, you know, how long between, so if they were to say green light, and they were to say red light right away, people always generally stop. But if they wait a little bit, then people get complacent. And then they say red light, then the people don't necessarily stop. Okay, so their x was sort of how long in between the go time and the stop time how the difference in time between them, and they feel that that should be, you know, a measure of trickiness, right? How tricky they've made the problem, right? Okay, so the x is some time difference with some time. So y was whether or not the person stopped them. X was time. Okay. So what we have then is they want to model the probability a person stops given this amount of time between when they flash them the go sign, the green sign, and when they flash them the red sign, the stop sign. Okay, so let's call that probability. The model for that is logit probability x equals y equals 1 given x is beta naught plus beta 1 x. So the logit, just to remind everyone, the logit is the log of the probability y equals 1 given x equals little x divided by the probability y equals 0 given x equals little x. So this is the odds, right? The probability divided by 1 minus the probability. Okay? So let's compare now logit probability y equals 1 given x equals little x plus 1 minus the logit of the probability y equals 1 given x equals little x. Okay, so what is this? So this is the logit of the probability that the person stops given a particular x plus 1 stopping time, a difference between the go and the red light and the green light. And this is the same logit probability, except the only difference is instead of x plus 1, we have an x in there, right? So it's the difference in the log odds of stopping for a 1 unit change, let's say a 1 second change in how long it took us to flash the red light after having flashed the green light. Okay, so let's see. So this, if you look at this equation up here, right, this is beta naught plus beta 1 x plus 1 minus beta naught plus beta 1 x, okay, which works out to be beta 1. Okay, so what is beta 1? Beta 1 is the difference in the log odds, right, the difference in the log odds for a 1 unit change in x. So beta 1 is the difference, the change in the log odds of a response of 1 given a 1 unit change in x. Or if x happens to be a factor variable, given a change from x from the reference level to the non-reference level. Okay? But notice, if we take e to the beta 1, right? So this is, look at these probabilities. So e to the beta 1, right? So this is e to the beta 1 is x of the log of the probability y equals 1 given x equals little x plus 1 over the probability y equals 0 given x equals little x plus 1 minus the log of the probability y equals 1 given x equals little x over the probability y equals 0 given x equals little x. Okay. Okay, so there's that. That's what e to the beta 1 is. Okay. So what does that mean? Well, x of log, right, gets rid of the log, and x of log gets rid of the log, and the difference of two logs is the ratio. Okay, so this e to the beta 1 works out to be probability y equals 1 given x equals little x plus 1 over probability y equals 0 given x equals little x plus 1, whole thing divided by the probability y equals 1 given x equals little x divided by the probability y equals 1 given y equals 0 given x equals little x. Okay? So what is that? That's equal to the odds that y equals 1 given x equals x plus 1 divided by the odds that y equals 1 given x equals little x. Okay? So, whereas beta 1 is the change in the log odds of success given a 1 unit change in x, and e to the beta 1 is the relative change in the odds, not the log odds, in the odds per 1 unit change in x, which is the relative change in the odds is called the odds ratio for obvious reasons, right? It's a ratio of odds. Okay? Okay, and then Scott asked with respect, well, just in the interest of time, I hope that kind of answers that question, but that's how you interpret an odds ratio. But actually, I'm just interested, so let me see. So, right. Sorry, I got to look up the quiz. It takes me a second. Where's the quizzes? Quiz, let's see, what was it? It was in quiz 4, question 1 through 3. Quiz 4, question 1 through 3. All right. Okay, I think so. For question 1, that seems to answer that question. Adjusting. Okay, so let's talk about what happens when you have an adjustment variable. Okay, so let's go back right here. Okay, so let's go back right here. Imagine we had. Wonder if let's see. This might turn out to be a disaster, but. Oh, not a disaster at all. Actually, and let's move it down here to a new page. Okay. So imagine instead of this equation, right, we had a z variable included plus, I need a pen, there we go, plus beta 2z, okay? Now, just repeat this exercise, but just hold z constant, right? So if I do logit, and this is now given x and z, right? Logit probability y equals 1, given x equals x plus 1, and z is held constant minus the logit probability y equals 1, given x equals x, and z holding z constant. So z is the same from this one to this one. You'll find if you plug into this that this is still equal to beta 1. So it just go back exactly through those arguments, and what you'll find is that beta 1 is the difference in the log odds comparing a 1 unit of the log odds of y equal 1 for a 1 unit change in x holding z constant. And then e to the beta 1 is going to be the relative, the odds ratio comparing y equal 1 to y equals the odds ratio for y equal 1 for a 1 unit change in x, but again holding z constant. So the interpretation of the coefficients is exactly the same. It's just you have to tag that extra line of holding the other variables constant. Okay. Oh, okay. And then for the third question is, I think, kind of interesting. Let me talk about the third question because I find it to be kind of important. So imagine if I fit a logistic regression model where I said the log that probability y equal 1 given x equals given x and z, given just x, over the probability, so the log of the odds, probability y equals 0 given x, right? That works out to be beta naught plus beta 1 x. Okay, that's the model I'm fitting. This right here, just by properties of logs, this is negative of the log probability y equals 0 given x over probability y equal 1 given x, right? We haven't changed anything, right? This is just taking this left-hand side and multiplying by negative 1, then multiplying by negative 1 again, which does nothing, okay? So this then is saying, just working with that equation, that log probability y equals 0 given x divided by the probability y equal 1 given x, right, that has to be equal to negative beta naught minus beta 1x, okay? Okay, so if your logistic regression is going to be consistent between treating the y equal 1 as the outcome versus treating y equals 0 as the outcome, if it's going to be consistent, then when you switch and treat y equals 0 as the success in GLM when you fit it, you should get the negatives of the coefficients, right? If logistic regression is consistent in that way, right? And if, at any rate, and it is consistent in that way, of course, right? It has to. It would be a major failing of the model if that weren't the case. But we see why it has to be the case, right? Because if we fit the log odds, right, the log odds considering a 1 a success is the negative of the log odds considering 0 a success. So the coefficients, if I treat 1 as a success, should be the negative of the coefficients if I treat 0 as a success. Okay, so that's actually a pretty thorough hint to question 3, I should say. Won't a partial derivative exactly define an interaction? Not 100% sure what this question means, but you're saying I'm thinking a little bit to try and guess, but I concede the point. What you're saying is that the interaction is defined exactly by the partial derivative of the two regression lines given the x variable. Totally conceded. However, the question is, how do you fit a model that fits a separate line so that the fitted model's partial derivatives, the difference in the partial derivatives is exactly the difference in those two slopes? Okay? So that's the question. And so I totally agree with you that if you have two regression lines and these are what the regression lines look like holding the other variables constant, then the way you could interpret the interaction term is it's the partial derivative of the expected response given x, and let's say in my previous example that the factor level equals 1 versus minus the partial derivative with respect to x given the expected value of y, and x given that the factor level equals 0. Totally conceded that is exactly how you, so that, I mean, but that is just another way of saying it's the change in the slopes between the two models. So yes, that is exactly right. However, I want, hopefully as part of this class, not to just understand what partial derivatives mean, which I don't actually think is necessary for this class, but to understand that when you fit the model with the interaction term of a factor level and a regressor, if you fit that interaction term in, what it's doing is it's fitting a model with two slopes. So now I appreciate the question. Actually, I understand your question now. I think it's a good point. Could you suggest a couple of good books to continue the study of regression? I'm not afraid of linear algebra. Oh, if you're not afraid of linear algebra, then there's a book by Myers. I always like this book by Myers, which is something like Classical and Modern Regression, I think is the name of the book. I like that one a lot. There's a book a classic book by Searle called Linear Models, and if you're interested in a book that has a whole lot of every detail laid out, maybe not in the most entertaining way, but every detail is definitely in there. Linear Models, that book's a classic. It's very rare for a statistics book to make its way into a paperback, but that one is. Let's see, and then there's this book with this kind of punny title called Plain Answers, but plain answers to complex questions. You should look at this one just for the title, by Christensen, that I like quite a bit. But the plain is spelled not like plain, it's plain the pun being that it's not plain as in simple answers, it's plain as in fitting planes, in the sense that regression models are fitting planes. So plain answers to complex questions. It's a complex question, I think, is the name of it. This book is by Christensen. So yes, so those are the books I would recommend. So Okay, let me get rid of some of these. I'm going to try and go down, prune these a little bit. Okay, so I think question 4 on quiz 3. Let me see this. Question 4. Okay, so would you be able to go over strategies for interpreting coefficient in multivariate regression? Oh, question 4 on quiz 3. I'm sorry. I was looking at question 4 on quiz 4. Question 4 on quiz 4. Question 4 on quiz 3. Oh yeah. Okay. So I think we talked about this one quite a bit actually. So I would, this whole thing streamed with all of its foibles and everything. So I would just look back. I think we went over that question pretty well. Okay. So let's see. This question belongs quiz 3. Oh, good, because I got quiz 3 up. Question 3, too. How can I test for the likelihood ratio? So it says fit the model with miles per gallon as the outcome and number of cylinders as a factor variable and weight as a confounder. Yeah, I would just suggest fitting the two models, doing ANOVA of the two fits, okay? But in this case, it's clear what you want to do with the ANOVA because one of the models is a subset of the other models. So one of them includes miles per gallon as an outcome, factor of the cylinder variable plus weight. The other one includes miles per gallon, factor of the cylinder variable plus weight, plus the multiplication of factor and weight. Now, I would just give you this one little hint. In R, if you do y tilde factor, let's say sil asterisk weight, this will fit the model. If you put this asterisk in there, there's a difference between putting in an asterisk and putting in a colon. When you put in an asterisk, it's going to fit the model that includes an intercept, cylinder as a main effect, weight as a main effect, and the interaction term between cylinder and weight. If you were to just put the colon in there, that just means only include the variable that's the interaction between the factor variable and weight. Okay? So the colon will give you just the interaction. The asterisk will fit the full model up to the interaction as well. What the question is asking you is for the asterisk version. Okay? And so, anyway, that makes that question a little bit easier. And if you put the colon in there, you're definitely going to get the wrong answer, because if you put the colon in, basically what it's going to do is it's going to fit a model that includes an intercept and just the interaction of cylinder and weight without the main effects. But otherwise, you should just be able to, fit the model that has an asterisk there, right? And then you want to fit the model that has a plus there, right? Because that only includes the main effects, and you want to compare the two with ANOVA. And in this case, because the latter model is a subset of the former model, I'm sorry, the model with just the plus there is a subset of the model with the asterisk there. The Anova function will work like I was talking about earlier. The test statistic and everything will be correct. Okay. Let's see. Fit LM miles per gallon is factor AM colon Cusack, data equals MT cars. I understand the coefficient of factor AM1, but what does factor AM0 Cusack mean? I'm going to have to actually load up the MT cars data set. I don't know what AM what the variable AM is. Let's see. Okay. And then let me actually fit the model that you're saying. Let's see. So fit equals LM MPG. Asterisk. I see what the point is. All right. Aha. Aha. All right. Here's the problem. What you've done is you've put the colon operator there when you should put the asterisk operator there. Okay. This is an interesting question. Okay. So you fit a model where it says y is equal to expected value y is equal to beta naught plus x, not x, beta naught plus factor 1 equal 1 times x, beta 1 plus beta 2 times factor equals 0 times x. And it turns out, so what does this model mean, right? So if factor 1 equals 1, this is a model. Yeah, this model is fine, but here's the issue. It's your model. What you're saying is I have. Let's see. So what does this mean? So f1 factor 1 equals 1. You get y expected value y equals beta naught plus beta 1x. And when factor level 1 equals 0, you get beta naught plus beta 2x. So what you've done is you've fit a model that has an intercept, beta naught, and it has two lines, but they come out of the same intercept, right? So this one is beta naught plus beta 1, beta naught plus beta 1x, and this one's beta naught plus beta 2x, okay? And that's totally fine, right? So beta 2 is interpreted as the slope. Beta 2 is interpreted as the slope when factor equals 0, when AM equals 0, when beta 1 is interpreted as the slope when AM equals 1, which is fine. I think the confusion is that you put the colon operator instead of the asterisk operator. If you fit the asterisk operator, it would do what we've talked about on numerous occasions. It would fit two lines with separate intercepts and separate slopes, and the coefficients would all be interpreted in the same way. So again, this boils down to, make sure when you fit these models, write out what the actual model is that you fit, and then as you play around with it, you can figure out what all the coefficients are interpreted as. But it goes back to this very important point about linear models, is the constraints that the model is fitting changes the interpretation of your coefficient. And what happened in your case is you fit a model where it didn't need a reference level, so it didn't do a reference level. Okay, so it said, oh, okay, what you want is two lines with the same intercept, so I'll just try and do that, and it gave you, gave you the slope for the first line and the slope for the second line, and in this case, there's no kind of computational or mathematical problems with doing that, so it just went ahead and did it. But this beta 2 is interpreted very differently than a beta 2. Or, if you had done the asterisks, it would have set that level to 0 because kind of mathematically it has to. So this boils down to being very careful in these linear regression problems with your coefficients, because you get quite different answers depending on what you do. Okay. Well, I'm afraid. I'm just trying to see if any one of these is. How can we deploy a shell? I'm just trying to see if there's some from other classes. How can we deploy a Shiny app in an Amazon web server? Okay, so Shiny is the name of the server that calls R in the back end. To run a Shiny app, you need a Shiny server, and that Shiny server, when you work on your app locally, that Shiny server is your computer, but it's just not deployed on the internet. But it's basically functioning like it's deployed on your internet. R is working as a little tiny web server for just your computer then. Okay? If you want it on the internet, someone needs to be running a Shiny server. In the case for the class, RStudio is providing the Shiny server for us. If you want to run your own Shiny server, then what you need is a web server, some sort of compute node that is on the internet that has the appropriate web services running. So what you need to do if you want to run Shiny server on Amazon is you need to spool up an Amazon cluster instance, an Amazon AWS instance. You need to install the Shiny server application on it. You need to start it up, and then you need to make sure all the ports are open that Shiny server calls when it's running. This is all given on the Shiny website on how to create and deploy your own Shiny server. How to create and deploy your own Shiny server, and then then installing apps on it, is not too bad. You just need to you need to know a little bit of Linux. Basically, here's one point I would tell you about this. If you don't know Linux, kind of cluster computing at all, or not cluster computing, if you don't know Linux web services and how to run like just a basic Linux box, then you have almost no hope of doing this. So your first step would be to learn Linux or Unix or something like that. Actually, it's Linux. It has to be Linux because they work on Shiny. Mostly the instructions are all for just 2 or 3 variations of Linux. And so if you're going to learn one of the ones that they have. Then second is you have no hope of doing this unless you actually know how to spool up Linux instances on AWS and run them and manage a cluster instance or an AWS instance remotely. If you can't do that, you have no hope in doing this. So the second thing to learn would be to learn AWS, which is the Amazon Cloud Compute. But then it doesn't matter whether it's Amazon or Google Cloud Project or Microsoft, which also allows you to spool up Linux instances. Any of those work fine. Then once you do that, you got to figure out how to install Shiny server. But that's pretty easy. If you use Ubuntu, you can use just kind of wget and deb. It gives you a Debian, a DB kind of application package that you can install pretty easily. For Red Hat, it gives you an RPM. So if you know what these words mean, then it's pretty easy, right? You can go through. If you want to use a non-standard distro that they haven't given great documentation about, then like someone on the class was saying they wanted to do it in Gentoo, and they got it working, but that person clearly just by reading their comments knew a lot of Linux cluster administration or Linux server administration. So anyway, what I would say is learn those 3 things if you don't know them, right? One is you need to learn Linux well. You need to learn how to do virtual machine management in one of the major virtual machine hosting services. It sounds like you want to use Amazon, which is actually not that hard to do, so learn that. And then third, you need to learn how to install Shiny on it. And then if you can get that far, then getting your app on there is trivial. You just SFTP your app onto the Shiny server and in the right place, and then it's just up and running instantly. Okay. So once you get to the point of getting everything running, actually deploying a Shiny app is just, it's trivial. It's just, Shiny server looks in a particular directory and user accounts, and in the subdirectories in those directories are Shiny apps, and then it looks for server.r and UI.r in those subdirectories, and that's it. But the documentation's all on RStudio's website. But that's a pretty advanced question. I mean, it would take me a full day or 2 to figure out how to do that. And I know a fair amount of Linux and know how to use AWS and stuff like that. So it's kind of a non-trivial endeavor, and that's why I think things like Shiny apps is a good solution, because you don't have to get into the um, the Linux server administration stuff, which is kind of a real pain. Okay, so another interesting question about machine learning. In machine learning, cross-validation is used to validate the model. Yeah, so cross-validate, yeah, I don't know. Machine learning cross-validation is used to validate the prediction. Often machine learning doesn't give you a very good model. I guess at some level they fit a model, but some cases not what I would describe as a statistical model. Either way, yes, cross-validation is totally useful in regression, and in fact, the leave one out cross-validation residuals, you don't actually even have to refit the model in regression, right? That's what, things like that make regression super easy. Having said that, it depends on your goal, right? If your goal is good prediction, then you need to do something like cross-validation to avoid overfitting. If your goal is to do a scientific investigation, then it's possible that you want to include variables that are poor predictors or unnecessary or whatever in order to explore the scientific question. As an example, I was working on a paper where I was looking at how does sleep disordered breathing predict hypertension. And of course, sleep disordered breathing is not a very big predictor of hypertension, right? You can get hypertension, your diet, your weight, these other things are much better predictors of hypertension. So if I were to build an algorithm for predicting hypertension, sleep disordered breathing would never be included. It would be cross-validated out immediately. However, because I'm specifically interested in the scientific question of when people have sleep disordered breathing, are they more likely to get hypertension than if they do not have sleep disordered breathing? Then I'm intensely interested in this one variable, and I don't care if the effect is small, I care if the effect is present at all. Then it's just a totally different setting. And so in that case, cross-validation isn't helping me at all, right? What's helping me is I need to do model selection. I need to do model selection by thinking about what variables to include and exclude, function of how they explain whatever relationship I'm seeing with sleep disordered breathing. Okay, so yes, absolutely, you're on the right track in that cross-validation is incredibly useful, but it's incredibly useful in a particular way for a particular set of problems, and it's just as useful if you're using regression to solve those problems as if you're using machine learning to solve those problems. And let's be honest, huge chunk of the regression and generalized linear models with binary regression, they'll usually get you 95% of the way there, and all the complicated machine learning stuff is getting you the last 5%. So regression is a great machine learning tool, and regression plus some model selection technique is a great machine learning tool, and feel free to use it. And yes, you should use cross-validation in that setting. However, I would say in the case of regression, there are all these other instances where you don't necessarily want to do cross-validation. You want to do something else. But thank you. That's a great question. I mean, that's a hard question, and you can probably tell by the way I'm answering it that I've thought some about this. And at any rate, I think this the prediction machine learning kind of revolution that's occurred in the past years has it often gets conflated with regression modeling strategies, which sometimes coincide with them and sometimes do not. So anyway, I think it's a very nice question. If you don't care about kind of generating parsimonious small models that are interpretable and exploring some scientific question, if you just care about good prediction, then actually a lot of the topics from the regression class go away. And you can, but then also it's not clear that it's not clear that regression is the best thing to do at that point. Then it might just be easier to fit some meta model that fits a bunch of things, regression included, and blends them together in some optimal way. But anyway, I thank you for the question. That's a great question. I apologize, but I'm a little bit past time, and I got to run. I'm sorry about the audio problems at the beginning, and I thank everyone for taking the classes. It's really fun for us. And just to let you know, so we're trying to improve the classes. I'm going to start next week with some re-recording for Inference and some re-recording for regression. to get the to get the sound quality and the production quality a little bit higher. Since you guys will have already taken the class, it's not as relevant for you. But if you want to refer back to the videos, if you look back on YouTube, I put all this stuff on YouTube also. If you look back on YouTube, there should be kind of better versions of the video in the future. Okay? All right, and thanks everyone.